Alrighty, folks, I think we are good to go. So let's begin now, module number 3. So we are past the halfway mark of the course. Really, there's only 4 more lessons to go. Shouldn't take that long to kind of get through at this point in time. Still a little bit of things that we are going to be new talking about, but what I would emphasize is it's really just a transition of things that we've already covered at this point in time, just reframing, and you'll see what I mean when we jump into today's lesson. So what we're going to be looking at for lesson 6 is we're going to be talking about generalized linear models, specifically dealing with count data. So what we're going to be focusing on is what's known as Poisson regression. So in business analytics, it is essential to model count data. And when we talk about count data, we talk about things such as the number of consumer visits, the number of accidents in a given period of time. This is the type of data that we are referring to. So this is now going to be our response variable is going to have a count aspect to it. So Poisson regression is widely used for count data when events happen at a constant rate. So in this lecture, what we're going to do is we're going to apply Poisson regression to, first we're going to start off with a synthetic data set. So we're going to create something that's going to have these nice little properties to begin with. So we'll be able to analyze that. So this is going to be representing the number of website visits in a, say, given day based upon 4 predictors, which we'll talk about when we get to that point in time. Also, there is a US arrest data set. So this is going to be crime data. We'll be using this towards the end to start looking at, well, when we have issues with the model, how do we adjust the model to be able to accommodate this, or can it even accommodate this? So we will also cover model diagnostics, hypothesis testing, and how to handle over dispersion. And this is going to be where we're going to get into some of those problems. So that is a lot for today, but we'll probably break this up into 2 parts to not overly kill these sort of things. All right, so a quick overview of generalized linear models, or GLMs for short. So generalized linear models are an extension of traditional linear regression models to accommodate response variables. So remember how the response variable beforehand followed a normal distribution? Well, that's not going to be the case this time. Specifically for what we're dealing with today, it's going to be following count data. So again, this is an extension of the traditional linear regression model to accommodate response variables that do not follow a normal distribution. So GLMs have 3 key components to them. So again, a lot of this is very, very similar to what we've seen with traditional linear regression. Again, it's just going to have a slight twist to it. So the first thing, and same as before, there is a random component to it. So when we're talking about the response, if we were talking about traditional linear regression models, we were talking about a response variable that followed a normal distribution. Here this time, it's going to be following a Poisson distribution because, again, we are dealing with count data. So for the random component, this specifies the probability distribution of the dependent variable, again, that response variable. So in the case of count data, the response variable is typically modeled as following a Poisson distribution. So with a Poisson distribution, we say each one of the y sub I, so our actual response value, follows a Poisson distribution, and the only parameter that the Poisson distribution takes in is that lambda sub I. So what is the average given a period of time? So what is the average for sub I, which I have right in here as it's just the expected value of I. So yi is the observed count, lambda I is the mean of that. Okay, I said we have 3 properties. That was only 1. The second is there is a systematic component to it. So this is the linear predictor. So again, exactly what we saw with our traditional linear regression, that aspect is still here. So we still have that beta naught plus beta 1 x1 all the way up to, say, some beta p xp. This is going to hold true. That linear combination of predictors is still going to be there. So that systematic component, that's exactly what this is. So this is the linear combination of the independent variables. Now we have this n sub I. This is eta. That is the Greek word for it. So this is just how we represent that linear combination of predictor variables. So in the past, what we've had was y was equal to this beta naught plus beta 1 x1 plus all the way up to beta p, we'll say xp. So we had that automatically because one of the assumptions that we had is that it was linear. So what we're talking about in terms of each predictor to the response, there was a linear relationship to it. So when we had this systematic component, which was on this side, we had this random component on this side. How we linked things together was, well, we just put them together. There was nothing that needed to be changed because those underlying assumptions were already in fact there. So we didn't really need to do anything. But here, this time around, what we're talking about is these y's, they are not following a normal distribution. So I can't just simply equate these two things together and say this is going to work. It's not, because it doesn't follow the same type of distribution that we would expect to see with the same sort of relationship that we have here. So how do we tweak this? And that's where the last part comes in. And oops, I've kind of drawn over this a little bit here. Is the link function. How do we link these two things together? How do we link that response? So do I keep the response exactly the same and just say y is equal to our systematic component, that linear combination of predictors? Well, again, if it was what we were dealing with before, that would be perfectly fine, but it's not in this case. So I'm going to have to take my response, I might have to transform it, put it through some function, and then through that function, I'm now getting that equality, and that's exactly what we have here. So the link function connects the mean of the response variable, so that's the lambda sub I in this case, to the linear combination of predictors, that's the eta sub I. So in Poisson regression, one of the ways we have of being able to link these two things together is we are simply just putting our output through the log function. So log lambda is what we have here, and this links to our linear combination of predictors. So do note there is a slight change. We're not saying that y is equal to this. Now, again, just to reemphasize this part beforehand, how we were doing things before. Well, what was y? Y was the average output that we would expect to see. It wasn't a specific predictor value. It was the average of what we would expect to see. So here, when I'm talking about the average or the mean, I'm talking about this lambda sub I, and that's what I am linking through this log function to the linear combination of predictors. So I'm saying log of lambda is equal to the beta naught plus beta 1 x1 plus beta p xp. Now this might seem a little bit off, but we'll play around with a couple of examples, and hopefully by the end of it, it will make a little bit more sense. But remember, what we were dealing with before when we were talking about specifically y is we were talking about what was the average output that we would get for these specific values of x's that we would put in. All right, so this ensures that the mean, that lambda sub I, is always positive, which again makes sense because if we're talking about count data, we're not going to have a negative amount of times of things happening. It could happen 0 times, it could happen 1 time, it could happen 2 times. But again, that's the whole point. It's not going to happen a negative amount of times. So putting that log lambda through keeps things positive in that regards. And it also counts, as counts cannot take negative values. There we go. All right, so what else do we have here? Where'd my mouse go? All right, so what is count data? Well, count data is frequently encountered in business applications. We may want to model how many times a consumer visits a given or in a given time period, or how many accidents occur in a given year. So Poisson regression is appropriate when the number of occurrences follows, and this is the key part here, follows a constant rate over a period of time and or space. All right, so count data consists of non-negative integers that represent the number of occurrences of an event within a fixed period of time, again, or it could be a fixed period of space. So examples of this are as follows. Oops, where is my... I lost my mouse, so clicking doesn't work. There we go. As we said, the number of website visits on a given day, sales transactions during a specific time period, and customer visits on a different marketing days. Do I have anything else there? All right. So for the first part of the lecture, we're going to use Poisson regression to model the number of website visits based upon a couple of predictors here. So we're going to have advertising spent, days of the week, the season, and new content published. So if we put new content up, are we going to see an increase in traffic? So this is going to be a data set that we are going to create. So you're going to be able to create this at home and get the same sort of output, hopefully, if you're playing along. This is not one that you have to bring in. Right. All right, so let's just talk about the model here for a second. So our Poisson regression model is going to look as follows. So remember, when we're looking at this y is equal to, what's y in this case? Y is log of lambda, where lambda sub I is what is the average at observation I. So again, we put that through the log function. And typically when we're dealing with this, we're just talking about ln. So log base E. Even though it hasn't specifically said it here, it doesn't really matter all that much. But just for easier terms and calculations, we just keep it as ln. So ln, the natural logarithm. So again, this is equal to your beta naught plus beta 1 x1 plus all the way up to some beta p xp. Now I do keep the i's in here just because I kept the I in here and it's up. But when we generalize this, obviously we're not going to be doing that. So lambda sub I, this is the expected count, so the mean of the response for observation I. We have our predictors, our x1 all the way up to xp, and of course we have the coefficients, so these are the population parameters, which we are going to try to estimate. Now, do keep in mind that how we interpret this is going to be different than how we interpreted things beforehand. Because if my model was simply just y is equal to some beta naught plus beta 1 x1 plus all the way up to some beta p xp, this model is easier for us to be able to interpret compared to the Poisson regression model. And why is that? Well, again, y is just the average outcome for specific given values of x. So if I wanted to know how my model changed if I increase or decrease one of my predictors, all I have to do is go to that specific beta. So for example, if x1 increased by 1, well, we see that y, the average, is going to increase by beta 1. If it increased by 2, then it's 2 times beta 1. And so on and so forth. So there is a natural way of being able to explain if I increase this predictor, this is exactly the change that's going to happen in terms of my mean average. But when we're talking about a Poisson regression, we're talking about log lambda. So in this case, if I were to increase, say, x1, again, we increase this by 1, so plus 1, then log lambda is going to increase by beta 1. Okay, but what exactly does that mean in terms of log lambda? Well, it's a little bit difficult to kind of just understand in this sort of regards. So we kind of have to undo things. We have to kind of get rid of that log to be able to do it. So when we start getting into the interpretation side of things, we're going to take a step back for a second. Well, how do we adjust this formula so that when we talk about it, it makes a little bit more sense? Because at this point in time saying, well, we're going to increase log lambda by beta 1. Okay, well, exactly what does that mean? If beta 1 is 5, what does it mean increasing log lambda by 5 actually mean for us? It's not, at least I don't feel that it is naturally as intuitive. So we're going to need to adjust from there. All right, what else do we have here? All right, so for exercise 1, this is going to be building that synthetic data set that we were talking about. So we're going to fit a Poisson regression model on the new synthetic data set with the number of website visits. This is going to be our response. Again, as the response variable, and 4 predictors, which is going to be advertising spent, day of the week, season, and whether or not new content has in fact been created. So remember before, when we were creating our linear model, we used the LM function. Here, because it's a generalized linear model, we're using the GLM function. So not a major jump in this regards. And in terms of the input for the function, we'll see it's going to be very, very similar to what we had already done. So it should not be a massive step or learning step in that sort of regards. So the GLM function fits the Poisson regression model. And of course, using the summary function on the model, same as we did before, provides the estimates for the coefficients, the standard errors, the z values, the p values, so on and so forth. So let's get down to that point there. And then we're going to talk about some of the assumptions that we need to make about the model in itself. All right, so let's jump over to my other screen. Here we go. So we need a couple of formulas to be able to do this. So not formulas, we need some packages in here. So the mass package, this is going to be for the negative binomial. We'll get to that towards the end when I say that when there are assumptions that have been violated in the model or something is not working out, what can we do to sort of correct that? So negative binomial is one of the ways of being able to do this, but we'll talk about that more when we get to that point in time. But let's bring that in now. And same idea, ggplot2 for being able to visualize some of these things. So running line 6 and line 7, I should also set, even though I don't need it right now, but just by default, set working directory to that source file location. I don't think I have any data that I need to pull on this, this lesson, but just in case. All right, so we're going to create a synthetic data set. So that means we are going to randomly create data values. So in order for you, again, I've said this beforehand, but I like to reemphasize these sort of things. For you to come up with the same data set, what we need to, since we're doing this randomly, is we need to set a seed. So we're going to do the set.seed function, and we're going to set it to 42. Why? Because 42 is a great number. So there we go. So what this means is the data that you are going to create randomly should look exactly the same as the data that I create randomly. Now, if we didn't set the seed because we were using these random functions, we would get completely different data. But for reproducibility, this needs to happen. All right, so let's set the number of observations. We'll call that n, and I'm going to set that to 200. All right, so I'm going to generate some predictor values at this point in time. So I said there's going to be 4 different predictors. So we have advertising spent, or ad_spent, day of the week, season, and new content. So for advertising or ad spent, this is going to follow a normal distribution. So I'm going to use the rnorm function. I'm going to use n as the number of random numbers that I want to be able to generate, so that's 200, and I want this to follow a mean of 500 and a standard deviation of 100, so it's not following a standard normal. Okay, so I have those values created. Day of the week, so what we're going to do here is we're going to use the sample function. So the sample function, it's either going to pick, because I'm putting in a vector here, the vector contains 2 things. It's either going to be workday or weekend, weekday or weekend. So the sample function will reproduce a new vector of size n, that's going to be 200, where the entries are just going to be randomly chosen between weekday and weekend. Now, I've been told that this typically follows a uniform distribution. I think for the vast majority of it, when n is large enough, it does really follow a normal uniform distribution, so everything kind of equals out in terms of frequency-wise. We're going to do the same thing with season, so it's either going to be a low volume season or a high volume season, again using that sample function. Now do note that the last argument in this one's replace is equal to true. Now what would happen if that was not set is that, again, I have a vector of 2 things. So if I'm talking about the vector of low and high, if the first time low is picked, low is removed from that vector, the only thing that could be sampled next is going to be high. As soon as that one was picked, there's nothing left in the vector to choose from. So we want a vector of size 200, but I only have 2 observations, so there's no way of being able to turn 2 into 200. But if I turn replace to true, that means as soon as I pick low, well, low's not going to be removed. It's still going to be a choice that's going to be allowed to be repeated. So that's really all it is. Replace just means repeatable. So let's create that one, and we are going to create new content, and new content is just going to follow a Poisson distribution. So we're going to use the rPois for that. It's going to be of size 200, and I want the average to be 3. So if this is for, say, 200 days worth of observations, the average number per day is going to be 3. All right, so now putting everything together, I'm going to create the model. So what we're going to kind of do in advance, and this is typically not what's happened, we go out and we collect the data, but here I'm creating the observations. I am creating the model in itself. So I'm setting the equation up for the model. I'm going to plug everything in, and I'm going to get the appropriate log lambda, and then I'm going to transform those afterwards. So my model is going to look something along the lines of this. And you can see this up in the top here. So this is going to be log of lambda is equal to, and here I am stating that my intercept is going to be 1.5. Advertising spent. So this is going to be, we'll say that's my beta 1, so plus 0.015 times advertising spent. We'll just do that as, actually, no, I don't want that. X sub add at the bottom. Then my coefficient for day of the week is going to be negative 0.0002 X sub W for day of the week. Season negative 0. Same idea, 3 zeros, 1 X sub D for day, and then plus 0.3, and this is going to be for new content, so X and C new content. There we go. So I've created at this point in time what I want my parameters to be. So that's my 1.5, my 0.015, my 0.0002, so on and so forth. So I've created those ones. We've created vectors now for all of my different x's. So I'm going to plug this into the right hand side, and this is going to generate 200 values for my log slash lambda. All right, so if I do all of this here, starting at line 17, let's run through this. Oh, sorry, these are already done. So I mean at line 23, so setting all of my parameters, my coefficients. Now I'm creating all of those log lambdas. So I'm saying the intercept plus beta times add spend, so on and so forth. Doing all of this. So that is done. Now what I want to do, so I've created a vector of size 200. Oops, here we go. Of size 200. This is all my log lambda. Oops. Log lambda. Now I just want those to be lambdas. How do I get rid of that log lambda? Well, I need to undo that. In order for me to undo the natural logarithm, I use e to be able to do that. So basically what I'm going to do is I'm going to take every single entry inside of here and just take e to whatever that power is, and what it returns is going to be lambda. So e to my log lambda, this just gets me my lambda. So that's what I'm doing in line 38 here. I am saying lambda, oops, where is my mouse? Lambda here is equal to e log lambda. And since log lambda is a vector, putting e to that vector is just going to go through each entry of that vector and just take e to that. So again, it's going to undo the log aspect, and it's just going to get me lambda. So what I'm doing right now is I am generating another vector of size 200. This is going to be a random vector following a Poisson distribution for these specific lambdas. So all we're doing right now is we've created a vector for log lambda. So we've undone the log lambda, so we just have lambda left, but that's the average output. So what I'm trying to do is I'm trying to create a new vector y here for my responses that follow a Poisson distribution with those specific lambdas. So that's what we're doing. We're calling that visits. So there we go. Now we're going to create a data frame. And that data frame is going to have columns visits, ad spends, days of the week, season, new content. And let's just print data out here for a second. So data, there we go. Close some of this up. So again, I have 200 observations. I don't want all 200, so I could have just done tail or something along those lines. So it tells me how many visits, advertising spent, day of the week, season, and how much new content was developed. So typically, when we go out and we collect the data, this data frame is what we would have. We wouldn't have a column already for advertising spent, days of the week, those sort of things. We would be going out and collecting the data that generates all of these sort of things. But because we created this example here, again, we're going to kind of reverse engineer it. So we've created this data set based upon this equation here. Can we get that same equation, or very, very close to that same equation? Because think of this equation is the underlying model for the data that we have. So can I recreate this based upon this data that we've created here? Hopefully that's clear. See, I always say that that's one of the major problems of trying to do these things online, is that at least when I'm in the class, I can be staring out. And if everyone's just sitting there going like, then I know at that point in time, we really need to rephrase things. We need to attack this from a slightly different angle. Here, I'm just looking at my camera. And I think my camera gets this. So I'm hoping that you folks get this too. But if not, always feel free to reach out. Office hours, all that fun stuff. Come visit. Yay. All right, so we have this data now. We have a data frame. We want to be able to now model this data. I want to be able to come up with this log lambda is equal to some beta naught plus blah, blah, blah. Again, what we have up top here, these are the actual beta. So again, we typically don't know these. We want to be able to estimate these. These are the true population parameters up there because again, we've created the data to have this. We know what the underlying model actually is, but again, we're pretending we don't. We have this data frame. How close are we actually going to get to this? Okay, so I'm going to create this model. I'm going to call it model using the GLM function. I'm going to say visits, there we go, is explained by, that's our tilde, ad spent, days of the week, season, new content, plus between all of these. Now, what is different than what we had beforehand is we have this family attribute here, and I'm saying it's equal to Poisson. So when we're going to be going through a couple of these other distributions, it's not always going to follow a Poisson distribution, but here, because we're dealing with count data, it is following a Poisson. So I just needed to set it to that, and data is equal to that data frame. So there we go. We've created the model. So beforehand, if we were doing this, we would have the data frame in itself. We would use LM for our function to be able to do this. So we have our data frame now. We're using GLM to be able to do this. And we're just specifically stating that the family of this is coming from a Poisson distribution. All right, same as before, we ran the summary on this. Summary is going to happen again. Whoops, that's not what I wanted. Let's make this a little bigger here. How we read these, similar to what we did beforehand. So they have their estimates. That's our second column here. We have our standard error, we have our Z values, and we have the P value. So if I was running the hypothesis test, asking the question, is the true population parameter for this equal to 0 or is it non-zero? So that hypothesis test is still here, and we can still run that just by looking at the P values. So if I'm looking at advertising expense, these two are categorical variables. Here it's a numerical following a Poisson distribution. I see that advertising spent and new content, these are very significant. When we talk about day of the week for weekend, or the season high and low, these ones aren't specifically that high. So what this could mean for us is it could still add something to the model. It's just not statistically significant. So the jump between going from a low season to a high season might not actually contribute all that much to the model. Same with the day of the week. Is it a weekend or a weekday? Again, differentiating between the two might not add something to the model in itself. So, all right. But we're not actually running the hypothesis test. But again, let's look at this. So what model did we come up with? And how does that relate to what we have? So what we came up with here, we have a log lambda, and this is equal to, well, what's our intercept? The intercept is 1.49 and change. So the true value here is 1.50, 1.49. We're really, really close with that. Then I have plus, shifting the decimal spot 2 spots. So this is 0.015, rounded to 3 decimal places. That's not bad, XAD. So these two things actually do line up perfectly there when we're trying to estimate. Awesome. Well, what comes next? Well, what comes next is we have negative, or sorry, no, this is positive. So plus 0.000686, so on and so forth. This is X days of the week for weekend. So these ones, again, this is so incredibly close to 0, that negative 0.0002 versus the positive 0.000686. Very, very small. How are they contributing things? Well, again, it's not the right sign, but again, since these values are so incredibly close to 0, yeah. What else do I have here? Then I have plus 0.0000990 XD. So again, these two incredibly close to 0. Again, we're trying to estimate. I think that would be fairly close. And last but not least, I have plus 0.3x new content. That matches up perfectly with what we have here beforehand. So the things that are statistically significant actually get really, really close. What's statistically significant? Well, my intercept, my XAD, so that's the advertising expenditure, and my new content. So those ones match up nicely. Everything else, it's still relatively close, but they weren't statistically significant to begin with. So this is the model that we estimated. This is the true population parameter of the model. So there we go. Let's see, where is my mouse? Here we go, coming back. All right, so a couple of assumptions that we need to go over. And why is this important? Well, it's important to understand the assumptions behind the model, because really misunderstanding these assumptions could lead to, well, we're dealing with business decisions. So this could be incorrect business decisions. If we are predicting a number of visits based upon new content and we overestimate what we're going to see because we're dealing with wrong assumptions, we could invest way too much money into a specific product when we're not actually going to get the return on that. So understanding what the assumptions are and what the limitations of the model are, these are key for us. All right, so Poisson regression comes with certain assumptions about the data that we need to check before applying the model. What are the assumptions? So the couple of key assumptions here that we need. First one being that when we talk about the response variable, it has to follow a Poisson distribution. So the dependent variable, the response follows a Poisson distribution. And part of a Poisson distribution is that the mean and the variance are equal to one another. So if the mean increases, the variance increases. If the mean decreases, the variance decreases. And this is typically where we're going to see a violation in these assumptions, that these two things are not going to hold true. How do we deal with that? What is the outcome of this happening? We'll talk about that in not too long there. Same as before, independent of observation. So observations are assumed to be independent of one another. So if we go out and we collect 200 data points, that there is no relationship between these things. It should be randomly done, which is when we created the data was randomly generated. Well, we set a seed. It's still random, but yeah, controlled random. The log link function. So what this should do. So when we were dealing with our traditional model, what we did is we did a scatter plot where we looked at, hey, this is one of our predictors and how does this relate to Y? Does it follow a linear trend? Awesome. So right now we know that the data that we have is not following a normal distribution, it's following a Poisson distribution. We still want that linear relationship to line up, but what are we doing? Well, we have to transform our response. So we're doing that log lambda. So if I'm looking at my log lambdas and I'm looking at a predictor and I'm doing a scatter plot of those two, then what I should find at that point is there should be a linear relationship with what we're trying to model here. So yeah, that's the three main ones that we have there. So independence, there's always the randomness that has to come from all of this as well. Okay. All right. So when we were talking about the mean and the variance having to equal to one another, well, what happens if it doesn't equal to one another? What happens if there is a violation of this? And this is where over dispersion comes into play. So over dispersion occurs when the variance exceeds the mean. So the data exhibits more variability than the Poisson model predicts. So again, the Poisson model predicts that whatever the average is the variance as well. So if the average increases, the variance increases. If the average decreases, the variance decreases, so on and so forth from there. So how do we deal with over dispersion when this does in fact come up? Well, there's two ways of being able to deal with this. And one of the problems with over dispersion is, think of it the same sort of way we're dealing with multicollinearity. So when we're dealing with multicollinearity, that overinflated the standard error, which decreased our test statistic, which increased our p-value. So it became difficult to trust our estimates. It gave us basically, when we're trying to do predictions, because the standard error also is inflated, the interval that we are dealing with the true value is also going to be overinflated at that point in time. So the same idea, we can kind of correct this a little bit. How do we deal with that one? That's actually part two of this. We can deal with a quasi-Poisson regression, which is just going to adjust, or it's going to kind of deflate that standard error. Now, what it's not going to do is it's not going to change the model estimates. So when we run that summary table, if we run it as a quasi-Poisson or as a Poisson, the estimates will still be the same. What's going to happen is that standard error is going to adjust, which is going to change the test statistic, which is going to then change the p-value as well. It's not an overly complicated way of being able to do things, but how can we tweak this a little bit? Well, another way we have of dealing with this is changing the distribution that we're using from a Poisson to a negative binomial regression. So what this is going to do is it's going to introduce a dispersion parameter for the extra variability. So you probably haven't heard of a negative binomial. We've heard of the binomials when we were dealing with the binomial distribution, the Poisson distribution, the hypergeometric. So this was our, I can't remember what chapter, probably like chapter 5 of when we were dealing with the Stat 261, or your first stat course when we first introduced probability. So these were our discrete, so they weren't the continuous distributions. So typically the negative binomial doesn't come up, but what was the binomial? The binomial was if we ran an experiment a certain number of times, what is the probability of a certain amount of successes? So with a negative binomial, we change the reframing of this is, well, how many times do we need to repeat this before we get this many successes? So if we're looking for 3 successes, the minimum amount of times we would need to run the experiment is 3 times. But if I want it within a given range, well, I might need to run it 10 times to be able to see 3 successes from there. So that's dealing with a negative binomial regression. We don't have that issue right now in the data that we have, but we will come up with that. There will be an issue of this shortly, so I'm introducing it now, so when we come back to it, it's going to make a little bit more sense. There we go. Still good for time here. All right, so testing assumptions of the model. So one of the things that we are going to be talking about is the deviance of the model. So the deviance is a measure of how well the model fits the data, and it's described as follows. Now, I'm not going to go through this formula because it's a little bit of a pain, but we say the deviance is 2 times. So I have a little bit of well, inside of a summation. So I'm going over all of my observations. So starting at observation 1 all the way up to my nth observation. And for each observation, I'm taking a difference here. So my first difference, what do I have here? I have what my true value is, my y sub I, divided by the predicted average of what would come from that. So that's my lambda sub I, and I'm putting this through log. And then I'm going to multiply that by the true value. And then what I'm doing from there is I'm saying, well, what's the difference between the true value, my predicted value for a given I, and subtracting that off. So again, y sub I is the observed count, so this is our true value. And lambda sub I, that is our predicted based upon the model. So again, our model gives us a lambda or a log lambda. We would need to undo that to actually get lambda back. And how do we undo that? Well, we take e to that because that's exactly what we did last time. All right, so a large deviance suggests a poor model fit. So the smaller the deviance, the better. Again, we're using this as how well does the model explain the variation that we have in the data. So for Poisson regression, if the deviance is much larger than the degrees of freedom, typically we have over dispersion. So if I go back to my screen here, one of these days I'm going to have a better way of doing this. Here we go. I'm looking at my residual deviance. So my residual deviance is 1.78889 e to the 2, which just means I'm shifting the decimal spot 2 spots to the right. So that's actually going to put me at 178.89. The degrees of freedom is 195. So these two things, if I look at the ratio between them, these are very, very close to 1. And if it's very, very close to 1, this is giving us indication that overdispersion is not an issue. So in terms of this model here, I would say that this model fits actually half decently well based upon that. We haven't run any hypothesis tests, but in terms of just making sure a violation hasn't been done, so far so good. Jumping back to the other screen. As soon as I find my mouse. There we go. All right, so Poisson regression assumes that the mean and variance are equal. So if the variance exceeds the mean, again, this is called overdispersion, and it violates the assumption of the Poisson regression. So that's where we need to check the overdispersion in the data set, which is why we're using the deviance to be able to help us do that. So what exactly is the test? Because I'm just saying right now, kind of a rule of thumb is if we're getting it close, or the residual deviance is close to the degrees of freedom, okay, that's good. But what is the actual test? So this is what we're going to talk about here, which is the goodness of fit test. Why is my screen? Come on, where are you? Mouse and mouse. There we go. The goodness of fit test using deviance evaluates whether the model fits the data well. So that is actually going to be our null hypothesis, is the model fits the data well. The alternative is there's a violation somewhere and it doesn't fit the model well. All right, so this test uses the deviance statistic to compare the fitted model to a saturated model, and that I mean a model with that perfectly predicts the fit of the data. So if we have 200 observations, we'd have 200 data points or 200 predictor variables inside of there, and we would hit perfectly every single time. So that would be our saturated model. Here we go. So our null hypothesis, H naught, the model fits the data well. The alternative is the model does not fit the data well. So this is actually one of those times where we're kind of hoping to fail to reject the null hypothesis. Because if we fail to reject the null hypothesis, then we don't have anything to say that this model is not the appropriate model to be using. All right, so assuming the null hypothesis is true, again, we always do this. We always assume that the null hypothesis is true. The deviance statistic follows a chi-squared distribution with degrees of freedom equal to the number of observations minus the number of parameters in the model. This is also including the intercept. So what is the rejection region? Again, we know we have a certain amount of deviance. Now, is that deviance too much based upon the degrees of freedom that we have? I said if we take the ratio of these two things and they're close to 1, okay, we're good. But again, how close to 1 does it need to be? So we're assuming that if the model is correct, this is going to follow a chi-squared distribution. So we're going to ask the question is, okay, following this distribution, assuming that the model fits well, I have this model that has this deviance in there based upon this degrees of freedom. What is the likelihood that I would see this if I ran this experiment again over and over and over again? So if the p-value of this is relatively high, then I have less evidence to support rejecting the null hypothesis, because that would mean that the probability that I would see this much deviance on this degrees of freedom when the assumption is in fact true, well, that's going to happen often enough. Now, vice versa, if it happens very infrequently, so a very low p-value, well, this is going to tell me that, you know, probably my assumptions on the null hypothesis here aren't in fact true, and it's more likely the alternative is in fact true. All right, so exercise 2, we want to calculate the deviance to the degrees of freedom ratio. So we're just going to compare the two. So the residual deviance to the degrees of freedom is, how close is that to 1? Would we, based upon that, assume that there is a violation of the assumption, which is the mean is equal to the variance, based upon the Poisson distribution here, or sorry, there's a violation, which means that there is overdispersion, or based upon the ratio between the two things, there's not. Well, we're going to run that hypothesis test. All right, so let's jump back over to R. Here we go. That was easier to find this time around. So I've already created the model. Model is just called model. I know. It's clever. No. Now I'm going to use the deviance function. This is going to get me my residual deviance, and I'm going to use the df.residual functions on my model, and that's going to give me my residual degrees of freedom. Now I'm taking the dividing by these two, so I'm taking the ratio of these two things, and I'm going to save this to deviance ratio, spit that out to the console, and it's 0.9173888. Okay, very close to 1, not perfectly 1. So meaning that there is a level of discrepancy here, but based upon this, since it's really close to 1, well, maybe I would assume that this is good. But let's run the hypothesis test. So this is kind of just a quick, cheap, easy way of being able to do it. If it's close to 1, awesome, probably don't have anything to worry about. But if it's far enough away from 1, okay, now we have to take a little bit of consideration here and actually run the hypothesis test. So if you can see above here on my screen here, H0, model is a good fit. And the alternative, issues with model. And of course, I haven't specified, but alpha is still going to be 0.05. All right, so let's run the test of being able to do this. There we go. All right, so again, I'm using the df residual and the deviance function. I don't really need to run these twice, but just for the fun of it. Now I'm going to find, well, what is that critical value? So here I'm running a chi-square distribution. I want 95%. So that's my first input is 0.95. So sometimes when I do this, I put in the 5% there. Sometimes I do this, I can put in the 95% there. Just have to remember that where it's looking at. So at this point in time, it's going to find a critical value, and where's that critical value where 95% of the observations happen to the left of that. Whereas beforehand, typically I would go lower tail is equal to false and say it's 5%. So it's like, what is that threshold where everything to the right of that, or the remaining right to that, is 5%? Either way, it works exactly the same thing. I just want to be able to find what that critical value is. Of course, I didn't spit that out, but I should spit that out. So critical value. So CV, that critical value is equal to 22 or 228.5799. All right, so what that means is if I were to run this experiment over and over and over again, if I got a residual deviance of 228.5799 or larger, this would only happen 5% of the time if the null hypothesis was true, if there was nothing wrong with the model. So only 5% of the time I should see extreme observations. This is my critical value. So anything to the right of this, I would look to reject the null hypothesis. So for us, well, our residual deviance, this is 178.89, give or take. It's approximately 179. So that's less than the critical value, so I would fail to reject the null hypothesis. Now I can also find out, well, what the p-value is. So looking at the p-value, oops. Oh, I can display them both here. Here we go. P-value is 0.7896845. So the probability that we would see 178 based upon this degrees of freedom, we should see it almost 80% of the time. Okay, that's often. So if we're supposed to see it this much when the null hypothesis is true, we would fail to reject, again, the null hypothesis, and we're not accepting, but again, leads us to that, there doesn't appear to be any major violation of the assumption. So looking at the ratio between the two things, it was incredibly close to 1. How close does it need to be? Well, based upon this, we still had a lot of wiggle room to go here. Let's look at this just for one quick second here. So if I took 228.5799 and I divided that by 195, 1.17. So the 195 is my degrees of freedom based upon this model. That 228 would have been my critical value. So if I had a 1.17 as my ratio between my degrees of freedom and my residual deviance, that's when I'd be running into a problem. So it still really is close to 1. So, it's not always clear as to when I should get rid of it versus not get rid of it. Fail to reject versus rejecting the null hypothesis based upon just looking at the ratio of the two. Okay, there we go. So in terms of the model following the Poisson distribution and over dispersion, that's the first parameter there. The second is the independence. The third is the linearity of the link. We can do that using a scatter plot. If I just look at, let's take log of lambda of each one of these. Let's look at the predictor. Do these follow a linear relationship? Awesome. Good to go from there. Okay, what else do we want to do at this point in time? A little bit of time left here before we get into the fun of this all. Here we go. All right, let's talk about interpreting the coefficients, because I said it's a little bit more of a pain to interpret them as is because we're dealing with that log lambda. So let's just say I had a single predictor variable. We'll say log of lambda is equal to beta naught plus beta 1 x. So if I increase x by 1, log lambda increases by beta 1. Okay, but what does that mean in terms of the model? Well, let's get rid of this log lambda. Let's just look at lambda. So if I take e to both sides, so this is e log of lambda is equal to e beta naught plus beta 1 x. I can break this up. Now, e and log, these are going to disappear. Again, log is the natural logarithm, so this just leaves me with the left-hand side of lambda is equal to e beta naught e beta 1 x. Okay, so now it's a little bit different because beforehand, what I had here on my my right-hand side was something that was additive. So my log lambda, if I increased x by 1, I would have an additive increase by beta 1. But here on my right-hand side, I now have something that is multiplicative. So I'm going to see a percent increase or decrease based upon taking each one of these estimates and bringing e to that power. So let's say I looked at e to the beta 1. If e to the beta 1 was greater than 1, so this is going to be some value. If it's greater than 1, well, what happens if I increase x by 1? So if x goes plus 1, then lambda increases by e to the beta 1. So if e to the beta 1 was, say, 1.25, the difference between 1, because multiplying something by 1 means it doesn't change, so 0.25, that would mean a 25% increase. Now, on the other hand, if e to the beta 1 was 0.75, that would mean my model is decreasing 75% of what it was beforehand. Or I can think about this in terms of, well, what's the difference between 0.75 and 1? Well, it's a difference of 0.25, but it's in the decreasing direction. So I would see a decrease of 25% if x increases by 1. So I'm going to see a percent change rather than an additive increase or decrease from what our original model is. But now this changes lambda directly, whereas before this changed log lambda. That's the difference. So additive, I'm changing log lambda. Multiplicative, I'm changing lambda. Again, I've written over stuff. So exponentiating the coefficients gives the rate ratio, which is the relative change in the expected count. So e to each one of these is giving us what's known as the rate ratio, which is the relative change per 1 unit of those specific values of x. So again, if x increases by 1, e to the beta 1 is going to be the change. So if it's positive, if it's greater than 1, it's a percent increase. If it's less than 1, it's a percent decrease. If it's 1, it's the same thing as saying, well, this really isn't adding anything to the model. It's like beta being 0 in the additive model, because multiplying by 1 doesn't change anything. Adding 0 doesn't change anything. So they're basically equivalent at this point in time. And as I said here, if beta 1 is 0.5, this means that for each unit increase in x1, the expected count increases by a factor of e to the 0.05, which e to the 0.05 is 1.65. But again, as I said, what's the difference between that and 1? Because 1 is something doesn't change. This is an increase by 0.65, or a 65% increase on the expected count, which is our lambda. All right, so for exercise 3, we're going to interpret the coefficients of our model. And then the last part for today, we're going to test the significance of the model. So kind of like we did beforehand, but we're going to more formalize the test here. So let's jump back. So exercise 3. What I'm going to do here is I'm just going to take the coefficients of my model. Now, I don't care about the intercept. I just care about, well, what is the change for each one of my betas. So here I have 4 predictor variables, so I'm going to have 4 different parameters in there. So I'm just going to take that -1, removing the intercept from there. So I'm grabbing all of my coefficients, and I'm taking e to that. So I have advertising expense is 1.015118. So this is greater than 1, so I will see an increase. What am I seeing an increase by? By 0.15118, so it's a 1.5% increase. So if advertising expense is going up by 1 unit, I should see a 1.5% increase in my expected foot traffic, or in this case, the expected number of hits per the website. Days of the week going to weekend. Again, I see an increase, but a very, very small increase. This is 0.0687% of an increase. So it's almost essentially 0, but it's not quite 0. There still is a percent increase here. Season low versus season high, again, same idea. It's very, very close to 1. So it's 1.000099. So this is a 0.0099% increase. New content. New content is 1.35. So again, greater than 1. How much greater than 1.35? So we see a 35% increase. So for each additional new bit of content that is created, we're going to see a 35% increase in traffic to the website. So out of everything here, by the look of it, that new content is the thing that's really adding a huge factor to whether or not people are going to be visiting the website or not. So again, if we spend more in advertising, we're only going to see, or 1 more unit of advertising, we're only going to see a 1.5% increase in traffic. Whereas if we put new content up there, 1 piece of new content is going to increase by 35%. That is a massive increase in comparison. So that's all about understanding the coefficients. Now, day of the week, weekend, these are all incredibly close to 1, which means, it's not really adding anything to the model in itself. Or making a huge difference in the model in itself, which also, if we look at the summary table, those are the ones that weren't really statistically significant, so they weren't really adding anything to begin with. So there we go. Last thing that we're going to talk about here, because we're 57 minutes in, yeah, it doesn't feel all that bad today. But at least for the first half of this, and then we'll get back to the second part of this afterwards. Testing the significance of this. So this is what's known as a wall test. So the wall test is commonly used to test the significance of individual coefficients. So same as before when we were doing that hypothesis testing, does beta I equal to 0 versus the alternative it's not equal to 0. We're doing this on a per coefficient basis. So it's not like I'm going to group things together. That was the, when I was looking to do that, that was the partial F test here. Again, we're just looking at parameters individually. It compares the estimated coefficients to its standard error to see if the coefficient is significantly different from 0. So our hypothesis test, no difference. Beta J equal to 0 versus it's not equal to 0. Now the wall test uses the wall statistic specifically. This is a slight difference of what you're going to see in the summary table. In the summary table, it doesn't use the wall statistic, it uses a Z statistic. This is an easy transformation, so we simply just keep the Z values rather than finding this, so it normalizes everything for us, which is helpful in itself. And that's exactly what we have here. So we can perform the Wald statistic by examining the Z values for each in the summary table output, which corresponds to the Wald statistic. The Wald statistic is just the square of the Z value. So that's it. That's all. All right, so assuming the null hypothesis is true, the Wald statistic follows, again, a chi-square distribution with degree of freedom being 1 because we're only dealing with 1 parameter here. So if the Z values follow a normal distribution under the null hypothesis, the summary table provides the respective p-value for a given Z value. So we reject H0 if the Z value is greater than the critical value, or again, if we're looking at the p-value, if it is greater than alpha. Yeah, do I have this here? All right. So we can manually compute the wall test statistic and compare that to the Z values, or perform the wall test for each predictor, which again, just running the summary table does it perfectly fine. So let's jump back over to R, and we're going to end it right after this little bit here. One thing I didn't do is this last little bit here. So this is going back to the last exercise again. Taking the coefficients of the model, taking e to those coefficients, subtracting the first one because I don't want the intercept. Now I'm subtracting 1 from that. So basically, if I was looking at that rate ratio, I was looking for a percent increase or decrease, this line would do exactly that for me. So running this line again tells me that advertising expenditure, for 1 increase in advertising expenditure, I'm seeing a 1.5%. So I've already changed these to percents. So 1.5% increase here. Going from a weekday to a weekend, I see a 0.1% change. Was that correct? Wait a second here. I said it was incredibly close to 0. Uh, 0.06. So yeah, this rounded it up to 0.1. Again, it's 0.1%. So this is not 10%, it's 0.1%. So that makes sense here. Season low going to season high, again 0 basically at this point in time, rounding to 3 decimal places, and new content is 35%. So that last little line just brings it to a percent increase or decrease. Again, if it's negative, it's going to be a decrease. If it's positive, it's going to be an increase. There we go. Let's see the coefficients. So what I'm going to do, because the first part asked me to manually calculate the Wald statistic, which is just taking the coefficients, squaring them, divided by the standard error squared of the variance here. So I'm grabbing a vector for the coefficients, I'm grabbing a vector for the standard error, I'm creating that Wald test, which is the ratio between the two, and I'm printing those out here. So I have my Wald test for each one of these. So I have advertising expenditure incredibly high, new content incredibly high, day of the week, weekend, or day of the week, seasons. These are incredibly small. Um, so what do I want to say about this? Well, again, I could pull up the chi-square distribution and find out what the critical values are, but oops, I hit the mic there, so that probably was kind of annoying for all of you folks there. Sorry about that. The higher these test statistics, the higher the Wald statistics, the more unlikely it is that we are going to, or sorry, the more likely that we're going to reject the null hypothesis and accept the alternative, which they are adding something to the model, whereas the smaller values here are more likely that we would fail to reject, which again, looking at that summary table of what we had beforehand, statistically the first and the last one, the advertising spent new content added something, the other ones didn't really add anything to it. Do I have all this stuff here? Yeah. All I'm showing with this last little bit here is if we grab the Z values and we grab the Wald statistics and take the square root of that, we end up with exactly the same thing. So I'm just showing you that if I'm reading off the summary table or if I'm actually calculating the Wald statistics by hand, it's all exactly the same thing. It's just easier for me to use the summary table. So if I was using the summary table based upon all of this sort of fun stuff, let's just go up here for a quick sec. Here's my summary table. And you can see from my screen above here. So if we do the hypothesis test, this is B. I is equal to 0 for I is equal to 1, 2, 3, and 4. First is the alternative BI is not equal to 0. And alpha being 0.05. There we go. So if we look at ad spent and its respective p-values, so this is approximately 0, which means reject H naught. If I look at day of week, p-value of this one is approximately 0.282. So fail. Fail to reject. Season S, approximately p-value 0.881. Again, fail to reject. And last but not least, new content. P-value approximately equal to 0, so reject H naught. So that was a very quick Wald test that we would have done for all of this. So we would do this exactly the same way we did beforehand. So a little bit more of a write-up for this, but that's the general idea. So not much has changed in there. I think that's good for today. That puts us at an hour and five. So we'll finish up the last couple of slides in the next lesson, which will complete everything that we need for this. So I'll have that posted in probably a few hours. So yeah, we'll see you back here soon enough. And here's my mouse. Stop recording.